Hello everyone, welcome to this lecture. Okay, so in this lecture we're going to see how solving linear equations, the process we use for solving linear equations, has a linear algebra view to it. How do these range and null space enter the picture, and how we can answer this question about what all inputs map to a particular point at the output. Okay, so let's begin by looking at linear equations and range. Okay, so here is a standard set of two linear equations and two variables, right? a11x plus a12y equals c1, a21x plus a22y a22y equals c2. We know how to write it in matrix form: a11, a21, a12, a22 times xy equals c1, c2. Now, this question, I hope you will understand, is the same as this question, right? If you have to solve this, you need to be able to answer this question. Is C1, C2, this is the same as that question, C1, C2 in the range of A11, A21, A12, A22? If it is in the range, then you have a solution. If C1, C2 is not in the range, you will not have a solution. Okay, so that's how range enters the picture of being able to solve linear equations. Okay, so how to determine this? You do elimination, right? So you take, you know how to do this. So C1, so you keep this matrix. You've seen solutions to linear equations. You write this matrix down, put a long line, put C1, C2, and start eliminating. And then you'll see the conditions under which something becomes 0 and non-zero. You know whether or not this is in the range. So that same process can be used to determine whether C1, C2 is in the range of this. Okay, so if this answer is yes, then one or more solutions will exist. If this answer is no, no solution exists. Okay, so this is the basis for this is the reason why this elimination process is important. And the elimination process is basically trying to find out if the RHS is in the range of the matrix here. Okay, and if it is in the range, you may have one solution or more solutions. Okay, so this also is something to remember. But if it is no, then there is no solution. Okay, so this is the way to answer this question. Okay, here are a bunch of examples. Okay, so I'm not going to go through this. We've done this in math 2, math 1 itself. Go back and check it out, and you know how to do this elimination. In this case, you'll have a unique solution. In this case, you'll have infinitely many solutions, right? This will be in the range and it'll have infinitely many, and here there is no solution. Okay, I'll leave this as an exercise. Please check it out. Make sure you practice and you're on top of this. Okay, it turns out there is a connection between the null space and the solutions of linear equations. This may not be immediately obvious. The range seems very immediately and directly connected, but why is the null connected? Here is a way to look at it. Let's say you have a linear equation like this, is two linear equations and two variables. Let's think of this matrix as a matrix representing a linear transformation T, right? A11, A12, A21, A22. It represents a linear transformation T, as in let's say canonical basis. So T of E1 becomes this A11, A21. T of E2 becomes A12, A22. That's how it is. So this transformation T will have a range and a null. Okay, and we'll assume for the sake of this problem, see that the C1, C2 is in the range of T. If it is not in the range of T, we know immediately there's no solution, nothing much interesting to do. Let's say it is in the range of T. What can we say about it? How does the null enter the picture? Okay, so here is the way in which it enters. Let's say by some method, okay, let's not go into the details of that. Let's say someone gives you a solution U0. It says U0 is a solution because it's in the range, and somebody gives you an actual input which goes to output. So T U0 is V. Okay, this has been given to you. Somebody gives it to you. Okay, right? Now it turns out, here is the interesting thing. If you take any vector in the null space of T and add it to U0, okay, I'm going to look at U0 plus U, okay, where U is anything in the null space, and what is U0? U0 is one solution to this equation. And if you do T of U0 plus U, what's going to happen? T is linear, right? I'm going to get TU0 plus TU. What is TU0? That's V. What is TU? It is 0. So I get V again. So if by some hook, some hook or crook, we found one solution, I can give you a whole bunch of solutions depending on null. T of U0 plus U is TU0 plus TU, which is again V. Okay, so this is how null enters the picture. Okay, so it just amplifies the solutions for you. Give me one solution, it can produce any number of, as many solutions as there are null. If there are no null vectors, then you won't get anything. There are null vectors in the transform, then you will get a multitude of solutions. Okay, so this guy, U plus U0 for all U in null T, is the set of all solutions for such an equation. Why is it the set of all solutions? Can there be any other solution? It turns out there can be no other solution. Suppose somebody gives you a solution, another solution W. Okay, u0 is one solution. If somebody gives you any other solution W, TW is V, notice what happens here. If you do TW minus TU0, you get T times W minus U0, which is 0. Which means what? W minus U0 is in the null space, right? So if W is another solution, U0 is one solution, W minus U0 is in the null space of T. If it is in the null space of T, then W better be U plus U0 where U is in null, right? So W minus U0 is U where that U is in null space. So W equals U plus U0. So I capture every solution by just saying U plus U0 where U is in null of T. Okay, so it's a bit technical, but you can see why this all solution get captured here. Okay, so here is illustration. Okay, so let's look at the illustration. Okay, so let's say range is R2 and null is the origin. Okay, so see, I'm in this R2 here, null space is the origin here. I'm interested in all the inputs which will get me to V here. Okay, this V is my target point. It's a red dot. I want to get here. I know my range is the entire R2, so I know there is some solution U0. Okay, then it has to come here. I know how to solve the equation. I'll get it. Okay. Now, what is my set of all solutions? To U0, I can only add 0, right? So in this case, the solution is U0 and it becomes unique. So notice this interesting thing. So if null T is the origin, then my solution is going to be unique. Okay. Is that interesting? So it's very interesting, I think. Okay, so if the null is the origin, then my solution is going to be unique for the linear system. Okay, it's a nice fact to remember. So this is how null connects to the solution for linear equations. Okay, so this is interesting. So here's another example. The range is now not the entire R2, but it is this gray line. Okay, it's a line. Okay, so if the range is a line, we know from our from the fact about rank nullity that null will also be a line. Okay, let's say null is this blue line. Okay, is that okay? Null is this blue line, and this gray is the range. Okay, I'm going to pick a point in the range. If I don't pick a point in the range, I have no solution. Okay, I'm going to pick a point in the range and ask, what is the solution here? Okay, so let's say some U0 I know will have to come here, isn't it? Okay, so some U0 will have to come here. Now, what is my result telling me? If I take this U0 and add the null space to it, when I add the null space, what will happen? I will shift this line to U0, right? Parallel to U0. It will shift here, and all points on this line will end up in the same V. Okay, so you have infinitely many solutions. Okay, so U0 plus this the entire blue line, you can see it will shift here, and you will get this line parallel to this blue line through U0. Okay, and the entire point, all those points will end up in this red dot. Think this through, why that is true. Very simplifying cases, supposing this red dot is the origin itself, then what happens? The entire blue line comes to the origin, right? The blue line is the null. Now, as you move the red dot away from the origin, this line that maps to that point also keeps shifting. Okay, so if you move this red point up and down this range, this white line will keep moving parallel to the blue line. So that's a good visualization to have. You have the null space and you have a point in the range. Now, what will be the set of all points that go from the starting R2 to that red dot? It will be a line which is parallel to this null line, okay, and going through one of the solutions. So as you move this null line parallel to it, you will get all the points on the range. Okay, so this kind of a picture of a linear transformation, it's very, very interesting to have. I hope you can visualize this. As I move the null space line, okay, the point here keeps moving on the gray line. Okay, so I hope you can see that. So that's the illustration for this way in which the null enters the picture here. So I hope this has given you a good feel for how to use the range and null, and have a linear algebraic view of solving linear equations. Thank you very much.